Hello, my name is Ian McCoyd, and I am a computer science undergraduate at Oregon State University. Today, I will be giving a brief talk about padding oracle attacks. This talk will cover the raw basics of symmetric encryption, then dive right into block ciphers and CBC mode before explaining how the padding oracle attack works, why it's a problem, how to fix it, and why it's still an issue today. We will also give a quick treatment of padding oracle attacks in the wild, and how an average attack will progress, giving a step-by-step process for how you could, or an attacker could, actually perform one of these attacks. I have a burgeoning interest in cryptography. I'm currently doing research under Mike Rosalek in the field of cryptography. Specifically, my research relates to linycrypt programs. The topic of padding oracle attacks is very interesting to me because I really think it exemplifies the idea that if even a single bit of information is leaked from your cryptography scheme, it can compromise your entire system. So seal up your buckets and get ready for this ride. Of course, we won't be able to give a full rundown of the entire field of cryptography in this talk, but this should act as a nice primer for what we need. Encryption is a process by which we help protect data by randomizing or scrambling the bits based off a secret value, so that anyone listening in on a conversation between two parties can't figure out what's going on in the messages, but both parties, the sender and the receiver, can still know exactly what the data packages mean. In our modern world, encryption has become ubiquitous. It's nigh impossible to conduct business online without using encryption. Just imagine sending your bank info or passwords as is over the vast internet. One form of cryptography is symmetric key cryptography. In this form of cryptography, we assume that both parties already have a shared secret key, and they can use this to encrypt and decrypt messages between them. Basically, the sender has a key by which they encrypt the message, and the receiver uses the exact same key in order to decrypt the message. You can think of this as if we were looking at like a rotation cipher. We can have the amount of characters that we're rotating by be the shared secret. This is contrasted with public key or asymmetric key cryptography. Protocols like SSL and TLS, which are used to encrypt your web traffic, use both of these in conjunction with one another. They start with a public key-based exchange of a secret, and then immediately switch over to symmetric cryptography using that secret for the rest of the traffic. They do this mainly because it's a lot less costly to send messages using symmetric key crypto. The use of symmetric key cryptography is important to us because it's one of the most common forms in the wild, and it's susceptible to our padding oracle attacks in many forms. We will be covering the attacks on block ciphers, but other error oracles can work on stream ciphers as well. Before we dive right into block ciphers, I want to present a basic overview of some of the tools that we will be using and talking about in the next few slides. In the slides to follow, you may see an operator which looks like a plus sign inside of a circle. This is what we call the XOR operator, or the exclusive OR operator. What it does is it takes in two Boolean values, A and B, and outputs another Boolean based off of the table on the slide. This operator is important to cryptography because not only is it reversible, but it's also uniform in its output. We can contrast the XOR operator with the AND operator. Now, what the AND operator does is it'll take everything to 0 except for 2 1. This is an important point to touch on because given a block of data, we can choose a second block to XOR the original block with so that the output is whatever we want it to be, as long as, of course, it's the correct size. It might be something that's not very easy to visualize in your mind. As we can see on the first line of the slides, basically how this is going to work is we are given a message, A, and we're given a wanted output, C. So we need to find a B so that A XOR B equals C. Now the cool thing is that using XOR, we can actually solve for B. And the property that allows us to do this is any message XORed with itself is always going to be 0. Just what we do is we just say, well, A XOR C equals B. When we do that solving and we set that as what B is, you can actually check. In the first equation, we have A XOR B equals C. So if we just replace B with A XOR C, we get A XOR C equals C. This will come up later when we cheat the padding system for CBC mode using a property called malleability. Another function class that will be thrown around is that of the pseudorandom permutation. Simply put, given an input x, the PRP will output another value from the same space as x, which will be indistinguishable from random data. But there's a little special property of that, of the output. If we just know the input, and we've never sent it through the PRP before, then we won't be able to guess what the output is. So we should not be able to guess what the output is going to be until we've already seen it. The following cryptographic methods have been created entirely using cryptographically secure functions. And even if the underlying functions are secure, that doesn't necessarily mean that you aren't going to get bit in the rear anyway. Block cipher modes represent a simple way to encode data. They are built using real-life versions of PRPs. How block ciphers work is by breaking down the message to be encoded into blocks of the same size, for example, 8 bytes or 16 bytes, and then encoding them one at a time. The most common block cipher mode at the moment is one called CBC, or cipher block chaining. In the diagram here, we can see how CBC mode works. It starts by taking in an initialization vector, or IV. So the IV is a random block, which is used to obscure the message. This makes it so that if we want to encode the same message twice, that information is not leaked to any people listening in on the conversation. It then takes a message and a key and sends all of that through a chain of block ciphers. First thing we're going to do is XOR the initialization vector with the first block of the message. And we're going to send that through the block cipher. The block cipher is going to be seeded using the key. This is the shared key that both parties need to have. We then call the result, the new initialization vector, to start the next chain. Decryption is effectively just the inverse of encryption. One cool thing though is that you don't need the plain text output of the first block in order to start decryption of the second block. What this allows us to do is parallelize decryption. In practice, it's actually a really great property. But you may have been wondering about the way that we break the message into blocks. Since not all messages are multiples of block length, how do we reconcile the difference between the blocks? How do we deal with blocks that come up short? That's where padding comes in. Since not all messages are the size of the block length needed by the block cipher function, we need to elongate those messages. This is the essence of padding. There are many different forms of padding, and for simplicity's sake, we will focus on the PKCS7 padding. As seen in the graphic here, how PKCS7 works is by computing the number of bytes that the message is behind the block length. For instance, if our block length is 16 bytes, but our message has size not divisible by 16, let's say 9 bytes long, then in order to make its length a multiple of 16, we have to pad the length by 7 bytes, which is the difference between the block length and the message length. These bytes have to be a specific form, so that the action is reversible after decryption. In PKCS7 padding, we add the number of missing bytes on the byte representation of the number of bytes that we need to add to the end of the message. So we start with message A, which is 7 bytes long, and our block size is 8, so we're missing 1 byte from message A in order to make it the correct length. We're going to pad A with a very specific set of bytes. Specifically, we're going to take the number of bytes missing, so in this case 1, we're going to put that into hex form, and then we're going to append that many, meaning 1, of those hex form representations of the number we're adding on. So in this case, hex form of 1 is 0, 1, and we need to add on 1 of them, so at the end of the message we put on 1 hex representation of 1. Let's take a look at message B. Message B is 4 bytes long, so we're going to have to add on 4 bytes of padding, and each of those bytes that we're adding on is going to be the hex representation of 4. So here's another case. Let's say that we have a message that is the correct block length. In this case, message C is 8 bytes long. We still need to pad it. The reason that we need to pad a message of the correct length is because let's say that we were unlucky and our message had padding at the end of the message. For instance, let's say that our message C was B with padding. The byte length of the message was 8, but it looks like the byte length was 4 because we have a bunch of padding bytes on the end. In order to get around this case, we are going to pad the message no matter what. That means even if the message is 8 bytes long, we're still going to pad on an additional 8 bytes. Now, if we were to try to decrypt a message that forgot to pad messages that were the correct block length, then we would end up removing actual information from the end of the message. Padding is a wonderful idea in theory, but there are actually a few problems that have arisen from shoddy implementation. In 2002, Sergei Vodinets presented one of the first padding oracle attacks on CBC mode encryption. This was a huge issue at the time, since it represented an attack on SSL/TLS. The padding oracle worked off of two main issues. The first was a malleability of CBC, and the other problem being a side channel inside of the decrypting portion of the CBC mode encryption scheme. Now that just sounded like a bunch of mumbo jumbo, but don't worry, we'll explain that. Malleability of CBC is integral to understanding the attack itself. Basically, how this works is, if you look at how decryption works in CBC mode, you will notice that the preceding ciphertext is directly XORed with the supposed plaintext. This means that we can affect the output of the system at any block by simply intelligently choosing a preceding ciphertext block. In the picture, we can see that this allows us to choose a ciphertext so that the last block of the message decodes to whatever we want. If you remember from a slide previously, we were talking about how when XORing two messages together, we can choose a B, or a thing to XOR the original message with, so that the output is whatever we want. We're actually given that opportunity. We can have the output message block for any part of the output be whatever we want it to. We could have it be all zeros. In that case, we've effectively guessed the correct message decoding. We can literally have it be whatever we want. Another big issue that was brought up in Vodinets' seminal proposal was that messages aren't being authenticated. When a message is sent to be decrypted, it's not being checked to see if that message is valid in its own right. When talking about the side channel, what a side channel is it an unintended information leak in the implementation of the algorithm. In this case, we can use such a side channel in order to get the result of M1 XOR A. We have cipher block 1 XOR message block. This is interesting because we just said, if we can have the message block output be all zeros, that means we'll have correctly guessed cipher block 1. Well, that being the case, if we can grab that, we can run this test as many times as we want until we get a correct cipher block 1, and in other words, gain the information of what cipher block 2 decrypted into, or we actually get the message itself. This is where the side channel attack comes into play, or in the same amount of arcane terms, the leaking of a single bit of information. If we could figure out what the last block of the message decrypted to, we could know the entire message, right? Well, this is where padding comes into play. The decrypting function is expecting some sort of padding. That's because no matter what we do, we're going to end up padding the message. So, to keep it simple, we're not going to go into HMAX at the moment. Basically, these side channels, or functions, in this case the oracles, would output one of two messages when decrypting. Or, more realistically, it would take more time to perform a certain path of the execution. Either the decryption method will output A, the message is valid or invalid, or the decrypting algorithm will output B, your padding was bad. Wait, so this is a big deal. We need to know what the message decrypts to on the server, but we can instead learn if the message decrypted to something with valid padding. Well, sign me up. We just need to find the correct previous block, or the second to last block, so that the last block's plaintext, XORed with the attacker chosen previous block, has valid padding. If we want to choose the correct previous block, we can then learn the contents of any block of the plaintext we want. Basically, we're going to end up iterating through all the single byte possibilities until we find one such that that byte XORed with the last byte of the plaintext is 0, 1. Pretty much how this is going to end up working is that we're given the encrypted message block that we want to decrypt, but we have no way of decrypting since we don't have this special key. And so what we're going to do is we're going to choose the block to send into the decryptor before it, so appending another block onto the beginning, but we're going to look at the last byte of our block that we chose, and we're going to just iterate through all the possible values until we find one that makes the block that we're trying to decrypt come out with valid padding. So this is only possible because of that property I was talking about earlier, where given any output that we want, we can find an input so that it matches it. So we're going to continue iterating through until we find the correct bytes that force the output to have a 0, 1 at the end. And that will give us the final byte for the message that we're trying to decrypt. So we can then, now that we know the final bit of the plaintext, we can repeat the process to find all other bytes in the message. Simply increase so that we XOR to get 0, 2 instead of 0, 1, and then with the previous block, iterate through all of the guessing until we get another 0, 2. So now the end of the decrypted block will be 0, 2, 0, 2. And we can keep on doing that until we end up with the full block. So we've got an 8-byte block, then we end up with a message that's A, which is the block that we chose, the malicious block, XOR B, which is the encrypted ciphertext that we either stole from eavesdropping or something like that. And we XOR those two together and we end up with 080808 8 times. So what that tells us is that we have A XOR B equals a bunch of 8s. But if we remember from a previous slide, we can now XOR both sides by our chosen cipher block. So we have chosen cipher block XOR chosen cipher block, XOR encrypted message equals a bunch of 8s XORed with chosen cipher block. So we end up canceling both sides and we end up with the actual decryption of the ciphertext, aka the plaintext. Now, you must be thinking to yourself, won't that take forever? What good is this attack? But this is the beauty of the attack. It's actually really quick. In an average crypto system, an attack on the key to the PRP will take 2 to the lambda operations, where lambda is the number of bits in the key. The attack we present here, the padding oracle attack, will give us a linear number of operations, which is simply, at max, 256 times the byte length of the message, which is negligible to the amount of operations needed to crack the key itself. We've come up with an attack that is many orders of magnitude faster, on average, than trying to attack the underlying cryptographic primitives of CBC mode. So we're pretty much throwing away all of the cryptographic work that people have done in the past in order to construct CBC mode and attacking something at the root, something in the implementation, which allows us to bypass all of that correct crypto. Now, this is all nice laboratory talk, but how would we actually do this attack in real life? Well, to be honest, it's not too much different from the laboratory attack. It just requires a bit more information gathering. First thing we're going to do is we're going to situate ourselves in some position where we can overhear a ciphertext message. That may be man in the middle attacking a private network, it may be poisoning a DNS system to send all of their information to us. Who knows what it's going to end up being, but we want to hear the ciphertext message that we want to decrypt. Then we have the issue of determining the block size. Usually the block size for these systems are either 8 or 16 bytes. There are cool tricks to figuring this out. One easy way, which often works, is that we just simply mod the message length by 16, and if it ends up being 8, the result, then we know that the block length is 8. Otherwise, the block length is unknown, and we'll have to go through a few other tricks. But after we've determined the block size, we're going to choose one of the blocks of the ciphertext, and we're going to, this is going to be the one that we want to attack first. This is going to be the one that we want to decrypt. Let's call this block Y. Then we're going to choose a few random bytes, call the set of bytes R, which is R1 through RB. For instance, if we're looking at a block with 8 bytes, that would be R1 through R8. We're then going to query the decrypting algorithm with R concatenated with Y. Now, here's an issue here. We're always going to assume that the message is not being authenticated. That is one of the underpinnings of the attack. So we're going to assume that the decryption algorithm is going to try to decrypt our message no matter what we send it. So we're going to query it with R concatenated with Y. Then it's going to try to decrypt it, and we're either going to end up comparing timings. Correct padding will take longer than incorrect padding, or we're going to look at error messages that are sent back from the server or from the function. And we're going to use that in order to categorize the results that we get back from R concatenated with Y being sent in into correct paddings and incorrect paddings. We then keep on repeating 4 through 6, XORing with RI until we reach correct padding, where I is going to be equal to B minus N, where N is the number of correct padding results that we have gotten so far. So for instance, we send in with R1 through R8, all random. Then we send in it again with R1 through R8, except for R8 is now XORed with 1. And we continue running through all of these XORs with the 8th byte in our random message until we get a result that says, hey, the padding was correct. Then we write that down and jump over to R7, and we continue the process. When we've gotten all the way down to R1 and we find the correct padding on R1, we're done. We found a introductory block, or a preceding block, that allows us to decrypt the entire block that follows that. So now we effectively have decrypted Y. Then we just simply repeat that for every other block that we need to decrypt. And then once we're done, we've decrypted the entire message. So the real problem here is not the vulnerability itself. These things just happen. I mean, at some point humans were still using Caesar ciphers. We get better, right? That's the issue. The attack still surfaces every once in a while to ruin our days. Not to mention the problems with people rolling their own crypto, and forgetting about problems that past implementations have run into. We also have the ongoing issue of backwards compatibility and legacy systems. In 2014, so this is 12 years after the seminal paper, an attack dubbed Poodle was unveiled, attacking SSL. Normally, when traffic is sent over the network, it will default to modern cryptography, or in this case it'd be, I believe, SSL 1.2. But it's possible to simulate conditions where the traffic will need to use an older version of SSL, SSL 3, for instance. Or in the general case, specifically not looking at SSL, in the general case, an older crypto suite. Then, all traffic sent by the affected system will be compromised if they're using a older crypto suite that is known to be vulnerable to these attacks. Another issue flowing about is the prevalence of these older systems themselves. Companies are the largest offenders in this category. With the costs of upgrading systems skyrocketing as upscaling becomes more and more costly, we see these companies using older systems for longer and longer, along with all the vulnerabilities that come with them. Cloudflare has been quoted stating that some 0.1% of its users are still using outdated SSL. But who knows what other outdated crypto the other computers are using? These things often compound on each other, so please, update your systems. Some notable examples of padding oracle attacks that don't focus on SSL are attacks on the Steam gaming client and CAPTCHAs. So the Steam vulnerability allowed for decryption of traffic and viewing of plaintext passwords in communication with the Steam servers. Steam was using a form of AES-CBC encryption for traffic. Basically, what was going on was that Steam would negotiate a shared secret with the user using RSA public key encryption, which was completely safe. Well, at least the time I'm giving this presentation, it's safe. I don't want to make any promises. Specifically, maybe with the advent of quantum computing, we may see a drop-off in RSA. Specifically, we may see the problem there is that we may have to double the size of our keys, but generally speaking, we can rely on RSA as a base. So Steam had two jobs. They needed to encrypt the traffic, and they needed to authenticate the traffic. This part was important. I want it to be completely transparent here. Encryption is not authentication. Steam did not adhere to this principle and forgot, or more likely, chose not to use a Mac to authenticate information sent to the server. Steam then made one more bad decision. It treated messages with invalid padding completely different than those which were just invalid as a whole. Steam ended up dropping all messages with invalid padding and airing messages with valid padding, but bad decryptions. This meant that we had a very easy way to determine an oracle. And since Steam wasn't going to authenticate before trying to decrypt everything fit right into place. All your passwords belong to us. The second hit on our list was CAPTCHA itself. Not the new Google CAPTCHA, but the olden CAPTCHA. Now, CAPTCHA was one of the most prolific techniques for preventing computer programs from submitting automated requests to servers. It revolved around showing a very distorted image of some numbers and characters, and then asking the user to tell the system what was actually written in the box. The premise was a computer vision problem, that computers shouldn't be able to distinguish the characters, since they were sufficiently distorted. We know now that certain machine learning systems can do this with ease, but at the time it was pretty much impossible. How CAPTCHA would work would be by sending a ciphertext to the user along with an image. Then the user would submit their answer along with the supplied ciphertext back to the server, probably in a hidden field, and the server would decrypt the real answer and compare it against the user-supplied answer. This, of course, did not stop users from altering the ciphertext given to them. Another issue was that no authentication was in place for the ciphertext decryption. This is the quintessential form of a padding oracle attack. This attack would have been avoided by keeping the ciphertext on the server, but the developers were lazy and didn't want to deal with the bookkeeping involved with that. So basically the user could keep supplying altered ciphertexts to the decryption algorithm on the server until they found the correct answer to the CAPTCHA. This effectively made the CAPTCHA completely useless, since now computers could figure out the answer to these hard questions for computers. You may have noticed a few things in common between these two examples of oracle attacks. In both cases, the server never authenticated the message before decryption. Now, this is where we can defend against the attack. How this is going to work is by changing the final steps of encryption and the beginning steps of decryption. We need to first pad, then add a MAC to the message after encryption. The decryption will follow as the opposite operation. First, we check the authenticity of the message with its MAC, then we immediately stop if it's wrong. Otherwise, we decrypt as normal. This is important because now the ciphertext can't be messed with. So, basically how this is working is that when a ciphertext is sent to the server, we were watching to see what path the ciphertext would go down. And we were supplying changes and changes and changes to these messages. Now, the trick here is that with our message authentication codes, if we send a altered message to the server, it won't send it down the decryption pathway in order to check for padding. It immediately drops it. It says, hey, this message has been tampered with, and drops it right there. Now, this is great because even timing attacks, where we're looking at the timing of the messages and trying to figure out what pathway it's going down, won't work, because every time we send a altered message to the server, it'll always take the same path, the drop immediately path, and we'll never be able to actually look to see if the padding is either correct or incorrect on the message. We still have that issue in the baseline of CBC with malleability, but specifically if we do encryption then MAC, or run it through CBC then MAC it, then we no longer have that malleability in the outputs, which is really key to secure cryptography. So, although this presentation was focusing only on software-based problems, another huge problem here is the physical side, or physical side channel attacks. People can watch physical changes on cryptographic hardware in order to determine what paths the operations are taking. So any problem that we saw on looking for timing attacks or looking at errors for looking for our padding oracle can be done on hardware by simply watching what pathways the hardware is taking when doing computations. This can immediately lead to an error oracle. The cool thing is that if we follow the ideas of authentication, the encrypt then MAC that we were talking about in the previous slide, then it's not a problem anymore. The encrypt then MAC doesn't just solve issues for software-based encryption, but also hardware-based encryption. So, in conclusion, padding oracle attacks are an interesting application of the idea that any information leakage is bad information leakage. Taking a single yes or no answer to provide a valid and quick way of decrypting arbitrary encrypted data and compromising the entire system. I hope all this information was novel and of interest to you, and I hope you enjoyed this presentation on padding oracle attacks.